How are you doing on this? Takes a while, doesn't it? Let's emphasize the key conceptual points again. So we're given a polynomial x cubed plus x plus 1 in fx, where f is z2. That is an, oops, not x sub 3, but x to the third power. That is an irreducible polynomial over z2 because it's got degree 3 and it has no zeros in z2. Right? F of 0 would be 1, and also f of 1 would be 1. Therefore, we know that the ideal generated by x cubed plus x plus 1 would be a maximal ideal in this ring. And therefore, if I form this factor ring, it will be a field. And technically speaking, this factor ring has elements that are cosets, where the coset representatives can be taken, this takes proof, but with proof, they can be taken to be quadratics. This is degree 3, so you can use a 1 smaller degree with coefficients in Z2, using this notation again. I wanted to avoid using the A because now that's what how the problem is phrased, is that A is the root of this in some extension field of Z2. A could be thought of as an element of here. In fact, A, based on things we said on Wednesday, A could be taken to be the coset x plus the ideal, right? We saw that that was a root of the polynomial. In fact, it was really a special case that we did of the general proof of Kroneker's theorem, fundamental theorem of field theory. Let f be a field, let f of x be a non-constant polynomial in there. Then there is an extension field of f in which f of x has a 0. The proof constructs that extension field as being that factoring, where you're modding out by the ideal generated by an irreducible factor of f of x. And it's x plus the ideal that is going to be shown to be the 0. So in essence, the A is playing the role of this coset, but you don't have to write it as a coset. We can think of the elements purely in terms of the representatives and do this really the same kind of calculations without bothering to write the ideal. Right, that's what this is really doing. And it is a field extension of Z2. It's got Z2 as a subfield, right? 0 and 1 is a subfield of this. It's got Z2 as a subfield, therefore it is a field extension. A is assumed to satisfy x cubed plus x plus 1. So this is assumed to be true, and therefore this is true, and therefore this is true when I mod by 2. And the only question is, if you make this set in this way and define multiplication in the ordinary way and use this fact, does it form a field? And it does. And this is the multiplication table when you ignore 0. This is the multiplication table of the non-zero elements. As an example, few example calculations, a times a squared plus 1 is going to be a cubed plus a, but then replace a cubed with a plus 1. And then don't forget to mod coefficients by 2. So a plus a is going to be 2a, which is 0. Therefore, this simplifies to 1. And then you could also say a inverse is a squared plus 1 would be another thing you could write because of that. Anytime you see an a to the 4th, you can replace it by a squared plus a. Okay, we've done these kinds of things before. It's just a matter of carrying out the details. This is the multiplication table for a group, right? The group of units of this field is a group. The field itself has 2 cubed or 8 elements. In fact, we're going to give it a special name. We're going to call it GF of 2 cubed, GF of 8. GF stands for Galois field. Galois spelled Galois. Galois field of order 8, 8 being a power of a prime, 2 cubed. Up to isomorphism, it's unique. And the non-zero elements, how many of them are there? There are 7, right? 1, 2, 3, 4, 5, 6, 7. The units under multiplication forms a cyclic group of order 7 because 7 is prime. I could write either U of GF8 for the group of units, or as is done in the book, write GF8 with a star. That also means the group of units, the non-zero elements, is isomorphic to Z7. It's cyclic of order 7. In fact, this is going to generalize. Any finite field that turns out will have an order equal to a power of a prime. And in fact, up to isomorphism, any 2 groups of the same prime power order are isomorphic. There's a unique field for each prime power order. The group of units, the non-zero elements under multiplication will always be cyclic, it turns out. What about under addition? This would be an abelian group under addition. I did not make the addition table, and we won't. What would it be isomorphic to under addition? It would have 8 elements under addition, right? Because you'd include 0 under addition. It would have to be either, well, it's abelian, so it's either got to be isomorphic to, so under addition, GF8 is either isomorphic to Z8 or isomorphic to the external direct product of Z4 and Z2, or the isomorphic to the external direct product of Z2 with itself with 3 copies of Z2. It's got to be one of those 3 groups under addition, because those are the only 3 groups of order 8 under addition. I should say those are the only abelian groups of order 8. There are non-abelian groups of order 8 that I'm not listing, but addition is commutative here. This fields are abelian groups under addition. So by the fundamental theorem of finite abelian groups, it's got to be one of these 3. Turns out to equal this one, or to be isomorphic to this one, actually. That's the answer. These other 2 don't work. And that's not so surprising, I guess. Effectively, each power of a to the 0 power, a to the first power, and a squared, kind of plays the role of, you might say, a 1 coordinate of an ordered triple. So for example, I'll add a rim on this paper here. For example, 1, 0, 0 as an ordered triple in this external direct product could be thought of as corresponding to the element 1 in Z2A. 0, 1, 0 could be thought of as corresponding to the element A in Z2A. And 0, 0, 1 could be thought of as corresponding to A squared. And this would also imply things like the fact that, well, you could say 1, 1, 1 corresponds to 1 plus A squared, if you like. That would be a natural way to match up these groups. Z2A being a group under addition. To ultimately show that, yes, under addition, GF8 is isomorphic to this external direct product. So it's not cyclic under addition. Is it difficult to find something like a to the negative 2 or a to the 100 power? Talking about the same field here. Well, a to the negative 1 we already saw because of this equation. The inverse of a is a squared plus a. A inverse is a squared plus a. Therefore, a to the negative 2 would be a squared plus a squared. And we could figure that out from scratch or use the multiplication table. A squared plus a squared looks like it equals a itself. Hey, how about that? A to the negative 2 equals a. Does that make sense? Oops, I did make a mistake. I thought something seemed funny there. This should be an a squared plus 1. A squared plus 1 squared is a squared plus a plus 1. A to the negative 2 equaling a didn't make sense because then a cubed would be 1, and we know that's not true. How about a to the 100 power? Well, one way to approach it is to remember here, this is a cyclic group. This is isomorphic to Z7. So every non-identity element is a generator. In particular, A is a generator. So this is just like a problem from chapter 4, essentially. Divide 100 by 7. What would you get? Divides evenly into 98. It's what? 7 times 14 plus 2. A to the 7th is going to be the identity 1. Write the identity as 1, the unity, instead of E. Oops. Looks like a to the 100 is a squared. If we wanted confirmation, if you wanted more confirmation that a to the 7th power is the identity, we could just keep doing calculations. We've already figured out that a to the 4th is a squared plus a, therefore a to the 5th is a cubed plus a squared, but a cubed is a plus 1. A to the 6th then would be, multiply all those by a squared plus a cubed, but again, a cubed is a plus 1. Mod the coefficients by 2. This is a 0 there. This is a squared plus 1. Hopefully here, now I multiply by a one more time, I get back to 1. This becomes a cubed plus a, multiplying that by a. And a cubed again is a plus 1. Yeah, that simplifies to 1. Mod 2. Kind of fun. Kind of. It's more fun probably than the reading, right? This reading is really tough. Doing calculations like this brings it to life. And you can think of either, again, for emphasis, you can think of either one of these as a field extension of Z2. Either one. They're isomorphic to each other. It's nice not to have to carry around the ideal all the time. So it's nicest to have it in this form. All right. If we're going to make progress on the content next week, our last week of class, including something called Galois theory, it'd be good for us to learn about what are called roots of unity. By roots of unity, I mean roots of the number 1. The number 1 being the unity. In the complex plane. Let's build it up by examples, okay? What's the first root of unity? That's simple. That is just the number 1. There's one first root of 1, and it's 1. Right? 1 to the first power is 1. And nothing else to the first power is 1. One first root of unity. There are 2 second roots of unity. Square roots. Plus or minus 1. Right? Those are the 2 numbers whose square is 1. How about third roots of unity? Turns out there are 3 of them. 3 third roots of unity. 1 is one of them. In fact, this pattern continues. 1 is always an nth root of unity. An nth root of 1 is 1, but it's not the only one, pun intended. What else, though? There's 2 more. I'll put question marks. How could we figure out what they are? Third roots of unity have to be roots of this polynomial. X cubed minus 1, right? That would make sense. Third roots of unity would have to be roots of x cubed minus 1. Is x cubed minus 1 irreducible over q? Or r for that matter? Got a guess? It is the difference of two cubes. That's a big hint. Is it irreducible? No, it's not. It's reducible. 1 is a root. X minus 1 is a factor. What's the other factor? It's worth memorizing, future teachers, that a difference of two cubes can always be factored, no matter what those two cubes are, in this kind of way. This is a special case of a more general fact of a difference of two cubes. If you call the cubes a cubed and b cubed, you can always factor that as a minus b times a squared plus ab plus b squared. You can check that. That works. So I'm applying that formula here with a equal to x and b equal to 1. So I guess the other two roots must be roots of this quadratic. Use the quadratic formula. See if we can figure out what they are. X squared plus x plus 1 equals 0. Use the quadratic formula. X is equal to -1 plus or minus square root of 1 minus 4 times 1 times 1 over 2 times 1. -1 plus or minus square root of -3 over 2. Those are complex numbers. That's going to be the same as -1/2 plus or minus square root of 3 over 2 times I. Those two numbers, those two complex numbers, are the question marks. Those are the other two cube roots of unity. Let's quickly check that one of them is. Let's check that -1/2 plus square root of 3 over 2 cubed is 1. This is worth doing once here. Multiply those two with FOIL, I'll get -1/2 times -1/2 is positive 1/4. Outside and inside terms are the same. They're both -1/2 times root 3 over 2, which is minus root 3 over 4. Two of those gives you minus root 3 over 2. I still, the i's in there. And then root 3 over 2i times root 3 over 2i is going to be minus 3/4. Right? Because I squared is -1. And then this simplifies to 1/4 minus 3/4 is -1/2 minus root 3 over 2i. Interesting. When I squared -1/2 plus root 3 over 2i, I got -1/2 minus root 3 over 2i. Is that an accident? No, it's not actually. And that's the other cube root of unity. Now multiply this out. 1/4. The outside and inside terms cancel. Product of those two things will be -3 root 3 over 4i. And the product of these two things will be positive root 3 over 4i. Outside and inside terms cancel. Last times last is minus 3/4 times I squared. I squared is -1, so this is 1/4 plus 3/4 is 1. And we are happy. the verification that negative 1/2 minus root 3 over 2i is a cube root of unity is the same kind of thing. 1/2, negative 1/2 plus or minus root 3 over 2i. Those numbers, 1/2 and root 3 over 2, feel very familiar, don't they? From high school. Trigonometry, right? Values of cosine and sine for special angles. It's not an accident. Pretend this is the complex plane. What is the complex plane? Well, it is a plane, two-dimensional space with coordinate axes labeled with the words real and imaginary. But the imaginary axis is there. I see it. It's there. I drew it. It's not. Well, I guess, I mean, it is still a figment of your imagination, but it's there. Any complex number, a plus bi, is naturally associated with a point in the complex plane with coordinates a comma b. A is called the real part and b is called the imaginary part, but even though we call b the imaginary part, it is a real number. A and b are both real numbers. In fact, the complex plane C is in fact R adjoin I. Right, it's a field extension of the real numbers containing I squared is -1. And I satisfies x squared plus 1. It's a two-dimensional vector space over R. Should always mention these things. This is a two-dimensional vector space over R. A basis consists of the two numbers 1 and I. You can write every complex number in the form a plus bi, where a and b are real numbers. Where are the cube roots of unity in this picture? They're on the unit circle. This is the unit circle. Radius 1 centered at the origin, and the origin, by the way, does represent the number 0. Where are the cube roots of unity? Well, one of them is 1. The other two are -1/2 plus or minus root 3 over 2i. Root 3 over 2 is about 0.866. Right around here and here are the other two cube roots of unity. And in fact, this angle right there is, as I hope you would guess, 120 degrees. 120 degrees, which in radians would be 2 pi over 3. And this one would be negative 120 degrees, or if I was after a positive angle, this would be positive 240 degrees. In radians, that would be 4 pi over 3. And 1 is at an angle of 0. These three complex numbers are all 1 unit from the origin. They are, you might say they have an absolute value of 1, and they are equally spaced in terms of the angles between them. It's 120 degree rotation from one root of cube root of unity to the next cube root of unity. More abstract algebra here. These three numbers form a cyclic group of order 3. And 1 plays the role of the E, the multiplicative identity. These two numbers are generators. And hey, that's why when I squared this one, I got the other one. When I squared this one, I got the other one. If I call this one omega, if omega is -1/2 plus square root of 3 over 2i, then omega squared is this one, -1/2 minus square root of 3 over 2i, which is also happens to be what's called the complex conjugate of omega, written with a bar above it, omega bar. Complex conjugate of a complex number, a plus bi, written a plus bi bar, is a minus bi. And a complex number and its complex conjugate have the property that when you multiply them, after foiling, you end up with a squared plus b squared, which is the square of the distance between a plus bi and the origin. You might say it's the absolute value of a plus bi squared. This is all stuff that's no accident. Call a complex conjugate here. Let's move on to fourth roots of unity. There are 4 fourth roots of unity. And actually, those are pretty easy. Plus or minus 1 and plus or minus I. And if you draw those 4 numbers in the complex plane, they are once again on the unit circle. And they're equal angles apart from each other. They're 90 degrees apart. 1i, -1, and -i. There are 5. Is the pattern becoming clear here yet? There are 5. 5 fifth roots of unity. What are they? If we believe the pattern continues, well, certainly 1 is one of them. If we believe the pattern continues, they should all be on the unit circle, and they should be equal angles apart. 360 degrees divided by 4 was 90 degrees. Evidently, they should be 360 degrees divided by 5 angle apart. 360 divided by 5, what is that? 72? Sound right? Yep. They should be 72 degrees apart on the unit circle, starting with 1. Something about like this. If you connect the dots, you get a regular pentagon. Fun, fun, fun. If you connect these dots, you get a square. If you connect these dots on the previous page, you get an equilateral triangle. Cool. But what are they? One, and I guess if we're going to make progress in writing these things any further, we have to pretty much just use trigonometry. Cosine, let's go ahead and use degrees, plus or minus 72 degrees plus I times sine of plus or minus 72 degrees would represent these two numbers. And cosine of a plus or minus 144 degrees plus or minus I times sine of plus or minus 144 degrees. And actually with cosine terms, you don't really need the plus or minus in there because cosine is an even function. And I don't need a plus or minus here if I've got a plus or minus there. I could actually get rid of the plus or minuses in both spots and have plus or minus signs in front of the i's, since sine is an odd function. Are these nice numbers? Tell you the truth, I forget. If these can be simplified in some nice way or not. Looks like they can. Although they are, the sign at least is a bit weird looking. Evidently, these can be written in terms of square roots. Let's get Mathematica to check that one of these really does work here. If I let omega equal cos 72 degrees plus I, capital I is the imaginary unit in Mathematica, sine of 72 degrees. And if I compute omega to the 5th power and simplify, I get 1. Here's something every math major should know. When you multiply two complex numbers, their distances to the origin get multiplied and their angles that they make with the positive real axis get added. If Z1 is a complex number with, well, polar coordinates R1 and theta 1, and Z2 is another complex number with polar coordinates R2 and theta 2. So R1 and R2 are the distances to the origin, taken to be positive, and theta 1 and theta 2 are angles for these numbers that the ray from the origin through these the number makes with the positive real axis. If this is Z1, that angle would be theta 1, and this distance right here would be R1. then the product z1 times z2 in C has polar coordinates r1 times r2 and theta 1 plus theta 2. Okay, that can be verified using trigonometry. In particular, coming back to these the fifth roots of unity here, and taking this thing to be omega, that's cosine 72 degrees plus I sine 72 degrees. Its polar coordinates are 1 for the radius and 72 degrees for the angle. If I raise it to the fifth power, the distance to the origin, the radial coordinate, stays at 1. 1 to the fifth is 1. What happens to the angle? It gets added to itself with 5 terms, 72 times 5, which is 360 degrees. That's why you're back to 1 when you raise it to the fifth power, because you've gone around 360 degrees when you keep adding the angle. 72 degrees plus 72 degrees plus 72 degrees plus 72 degrees plus 72 degrees. We said the third roots of unity form a cyclic group of order 3, with these two elements being generators. The fourth roots of unity form a cyclic group of order 4, but not all those numbers are generators, not even all the ones that are not 1. -1 is not a generator. I and negative I are the generators. With the fifth roots of unity, they form a cyclic group of order 5 under multiplication. Any one of the ones that's not equal to 1 is a generator. Let's do one more. Let's do 6 roots of unity. There are 6 sixth roots of unity. (360 degrees divided by 6 is 60 degrees. They're all going to be 60 degrees apart. 60 degrees is a special angle. Cos 60 degrees is 1/2. We're going to get 1/2 plus or minus root 3 over 2i. We also have plus or minus 1. And plus or minus 1/2 plus or minus root 3 over 2i. Those two happen to also be third roots of unity, but they're also sixth roots of unity. Let's do one more. Let's skip seventh roots. Of course, I could do it. The angle would be 360 degrees divided by 7, whatever that happens to be. We'll skip that. We'll do eighth roots of unity. And by the way, when you graph these, they're on a hexagon. For the 6 roots of unity, when you graph the 8th ones, they're on an octagon. Plus or minus 1, plus or minus I, and what I'm about to write next is going to correspond to 4 different numbers. Well, let's write it in 2 pairs. Square root of 2 over 2 plus or minus square root of 2 over 2i, and negative square root of 2 over 2 plus or minus square root of 2 over 2i. Quick graph. Graph the 6 roots. Going to be about like this. And they do make a hexagon. Graph the 8th roots. There they are, and it's going to make an octagon. Those from a cyclic group of order 6, there's only 2 generators, though. Omega and omega bar are the 2 generators there, if omega is this one. This is a cyclic group of order 8, there'd be 4 generators. Any one of these 4 would be generators. In general, there's something called the primitive nth root of unity. That is going to typically taken to be the one with the smallest angle. That's not 0 degrees. It's not equal to 1. It's going to be cosine. If I use degrees, it's 360 degrees divided by n plus I sine 360 degrees divided by n. If I use radians, you write that as cosine 2 pi over n plus I sine 2 pi over n. And because of something called Euler's identity, which says that e to the I theta is cos theta plus I sine theta, we can write all these roots of unity in terms of the number e. And in particular, this one is going to be e to the I times 2 pi over n. And all the properties of multiplication that I mentioned, well, the fact that the radial coordinates get multiplied and the angular coordinates get added in polar coordinates, correspond to properties of exponents here. Ever seen Euler's identity before? A few people know, a few people yes. This is a very famous identity in math. Every math major should know it. It's a mystery as to why it's true. It can be derived actually using Taylor series. A very, very important fact in math. It's also related to the most beautiful equation in the universe. In fact, you might say Euler's identity is the most beautiful equation in the universe. But if you plug in theta equals pi, you get e to the I pi equals cos pi plus I sine pi. Cos pi is -1, sine pi is 0. So therefore, e to the I pi plus 1 equals 0. And that is the most beautiful equation in the universe. And aliens would agree. If you get abducted and they say they'll let you go if you tell them the most beautiful equation in the universe, well, there it is right there. Why? Because it's got the 5 most important numbers in the universe. 0, 1, e, I, and pi are the 5 most important numbers. It's got the 3 most important operations: addition, multiplication, and exponentiation. And it's got the most important equivalence relation, equals. Fun, fun, fun. The most beautiful equation in the universe comes from Euler's identity. And we can represent all these answers in terms of Euler's identity if we want, in terms of E. So this is all background stuff that's not explicitly taught in chapters 20, 21, 22, but is going to be helpful for us as we continue working through examples next week, including some examples on Galois theory. And that's our last chapter is on Galois theory. All right. Have a good weekend.